Let me get this straight. A protein is just a chain of amino acids, but somehow it folds into a shape that makes all life possible. What biology calls proteins seems suspiciously like magic, but fear not, it's only science.
Or is it?
So, these things called proteins are actually long chains of amino acids. Imagine them like Legos that need to be ordered in a certain way to perform a function. If they're ordered incorrectly, the final build can't complete its function. Now, figuring out this dance for each protein used to be a slow and costly puzzle, with methods such as X-ray crystallography, involving shining X-rays on the crystallized protein to produce a diffraction pattern, or the unique set of spots or rings that forms when X-rays scatter off of the atoms in a crystal, helping to map out the protein's three-dimensional structure. NMR spectroscopy, which stands for Nuclear Magnetic Resonance Spectroscopy, and uses magnetic fields and radio waves to analyze the magnetic properties of atom nuclei in proteins, revealing their structure and dynamics in the solution. And electron microscopy, which images proteins at high resolution by firing electrons at them, allowing for a visualization of their structures, which is particularly useful for large complexes of proteins that are very hard to crystallize. Each protein has its own unique fold, dictated by the sequence of amino acids. But how do we predict this without spending years in the lab? Enter AlphaFold 3. It's not just about predicting where proteins fold, it's about understanding the dance of life at a molecular level. AlphaFold 3 uses deep learning, training on vast datasets. We know that AlphaFold 2 has trained on over 170,000 protein structures from the Protein Data Bank, and though AlphaFold 3's training specifications have not been disclosed, we know that it utilized datasets with approximately 30% more data, including a significant increase in large protein complexities of known protein structures to predict new ones.
Now, I get that this might sound incredibly complex right now, and you might be wondering how AI can handle all of this. Well, the simple answer to this question is that AI handles proteins similarly to other AI models such as the ones in social media predicting what content you might like. This classification of an AI model is known as a predictive model. A predictive model is made by first collecting data. In the context of AlphaFold 3, the protein data is collected from the Protein Data Bank. Then, the data is cleaned by filling in gaps, correcting anomalies, ensuring each piece is ready for our AI to learn from. Then we can transform this raw data into a feature through normalization to make sure that our AI can quote-unquote digest it properly. After the data is all set, we have the most important part of making an AI model, the training. With clean and structured data, it's time for us to train our model. The AI uses algorithms such as decision trees, neural networks, or support vector machines to learn patterns and relationships in the data. This process involves feeding the data into this model, adjusting its parameters, and iterating this until the predictions are as accurate as possible. For example, a neural network might be perfect for recognizing faces in photos, while a simpler regression model could work for predicting sales trends. It's like practicing a sport. The AI plays the game over and over, learning from its mistakes and improving each time. Now that our model is trained, it's crucial to validate and test the model. This ensures that the AI can perform well on new, unseen data. By splitting the data that we started off with into training and testing sets, we can measure how accurately the model predicts outcomes. Think of this step as a dress rehearsal. We want to make sure everything works before the real performance. And there you have it. This is the journey of training a predictive AI, such as AlphaFold, from raw data to a polished, powerful model that can achieve remarkable scientific achievements. Ultimately, this returns us to the question, why use AI to figure out the fold of proteins? Well, it turns out AI is just better at this than humans. According to a paper AlphaFold achieved an accuracy of 0.96 Armstrong root mean square deviation at 95% residue coverage, while the next best performing method only scored 2.8 Armstrong root mean square deviation. Given that the accuracy is higher when the Armstrong root mean square deviation is lower, we can see that AlphaFold has achieved remarkable efforts. As well as this, it has deeper implications on the use of AI in science. AI never used to excel at math and science subjects, but now through AlphaFold, we've realized that AI is a powerful tool for us to understand our world and our human race.